get covalent bond. Okay, so we already learned how covalent bond is formed. Does anyone know? Does anyone remember how covalent bond is formed? Is it formed by sharing or is it formed by transferring electrons? Covalent bond. Sharing. Okay, and there's a special type of covalent bond known as dative covalent bond that I want to discuss with you now. So put it on a new page. So types of covalent bond. Right. First, put that. Yeah, recall that covalent bond is formed by sharing of electrons. So covalent bond is formed when atom shares electrons between them. Okay, so when atoms share electrons between them. There are, however, two ways atoms can share electrons. So one is when they share or contribute to electrons equally. Okay, one is when one of the atoms contributes to all of the electrons. So there are two ways for that. So there are two ways sharing of electron can occur. So sharing of electron can occur. The first is when you have two atoms and the two atoms contribute equally. Like for example this. So you have let's pause. Okay, just a moment. Okay, I don't know what happened. What's right there? Okay, so that doesn't happen. So there are two-way sharing of electron can occur. So the first is when the atom contributes to electron equally, like this. Okay, so you have atom A, you have atom B. The first is when the two electrons, okay, they are contributed by the atoms equally, like this. So the second is when one of the atoms contributes to both of the electrons, okay, like this. So what is the difference between the result here? Okay, it is that in the first case, the two electrons, okay, each come from one of the atoms. Okay, so there's one electron coming from one of the atoms. But in the second case, both of the bonding electrons comes from just one of the atoms. Okay, so can you highlight these electrons here? Remember what we call electrons found in between atoms? Do we call them bonding or non-bonding electrons? Bonding electrons, okay? So can you put down case 1 here? Write down what is this about? So case 1 is where both bonding electrons, okay, so the bonding electrons come from both atoms, okay, contributed by equally by both atoms. So the bonding electrons are contributed by the two atoms equally. Okay, so by the two atoms equally. Underline the word equally. In case 2, so in case 2, both of the bonding electrons are contributed by just one of the bonding atoms only. You see the other atom, look at B. Did B contribute to anything to this bond? No, right? Look at where the electrons in between A and B come from. They both come from A. B has nothing to contribute. This is the second way in which the covalent bond can form. Okay, so second way through which the covalent bond can form. So bonding electrons are contributed by just one of the two bonding atoms. Okay, so one of the two bonding atoms. So can you also put that A and B here? I almost forgot. So you can see that in case 1, the bond is contributed equally, okay, by the two atoms. In case 2, the bond is formed by the sole contribution by just one of the atoms. So they are not the same. So they are not the same. This bond on top, we call it a normal covalent bond. So this bond on top, can you label this as a normal covalent bond? you find below is called a dative covalent bond. Okay, so this is a special type of covalent bond known as dative covalent bond. And when we draw a normal covalent bond, we just use a single line, right? Do you remember? We draw a line to represent a covalent bond. So in here, we can simplify the diagram as A, and then a bond, or stick, and then B. Okay, so the line represents a normal covalent bond. So a line represents normal covalent bond. So how do we represent the dative covalent bond then? We use an arrow, we draw an arrow, okay? And the arrow has to be pointing from the donor to the recipient. So can you tell me which of these two atoms, A or B, are the donor of the electron pair? A. So therefore we will draw an arrow pointing from the donor, which is A, to the recipient, which is B. Okay? So can you put down an arrow? Okay, represents dative covalent bond, and it always points from the donor to the recipient. Okay, so write down this guy here is the donor of the electron pair. So this is the electron pair you see it here. Okay, so both of the electrons came from A, so we call him or her or it the donor. This we call it the recipient. So recipient of the electron pair. So dative covalent bond, normal covalent bond. Okay. Now, let's take a look at some examples. Okay, of normal covalent bonds and dative covalent bonds in molecules. Okay, starting with ammonia. Have you all heard of ammonia before? Do you know what ammonia is? Ammonia. Never heard of it, but you do know water. Right? Water is H2O. So yeah, you can finish copying the standard. So the two types of bonds. Oh, there's an extra note I want to add below. So write this down, please. So the two types of covalent bonds differ only in the way they are formed. Okay, only in the way they are formed. So the two types of covalent bonds differ only in the way they are formed. Once they are formed, though, they should be treated the same as any other bonds. Okay, so they should be treated the same way. Okay, they behave similarly chemically. So the two types of covalent bonds differ only in the way they are formed. Okay. Once formed, they are indistinguishable from one another. So once formed, they are indistinguishable from one another. Okay, so indistinguishable from each other. Let me explain with some examples on the right first. Starting with ammonia. So ammonia is NH3. Okay, so can you all try to draw NH3? So this was not on the homework. So I want you all to try now. NH3. Okay, knowing that N has like a 5 outer mole share electron, H has 1 outer mole share electron. So here's a short task for all of you. Draw ammonia, NH3. I'll give you some useful information. N has the atomic number 7. H has the atomic number 1. Don't forget that you have 1 N and 3 H's, okay, in NH3. And I'll give you some additional hints. This is how the N and H arrange themselves in space. Like that. Okay, so you have N at the center and you have H's on the side. Can you help me complete this drawing of NH3? Knowing the atomic number to be 7 and 1 respectively. You have to take the same steps we took last time. Turn it into electron arrangement. Step 1 is to turn the atomic number Z into electron arrangement. What's the electron arrangement of nitrogen?
2,5.
2,5. Okay, so can you write down 2,5? What about hydrogen? Obviously, just one. And we only show, I noticed that in your homework, some of you did not remember that you only show the outermost shell. Some of you drew also the inner shell. You shouldn't. When you draw the covalent bonds, you only show the outermost shell. Okay, so Therefore, you only show these outermost shell electrons. So for nitrogen, you have 5. For hydrogen, you have 1. And make up your mind which symbol to use. It's entirely up to you though. Okay, I'm just using dots for nitrogen and cross for hydrogen. You can swap them. You can use triangles. You can use other symbols, but circle and cross they are most common. Now, can you help me put the dots and cross in a certain way? Okay, to ensure that all the atoms they have a full outermost shell, all of them. Great. So we'll check the answer in 20 seconds. How do you put the 5 dots of nitrogen and the 1 cross of hydrogen in these circles so that all the atoms they have a full outermost shell? Well, how many do we put in each overlapping space here? Right, don't mind. That's why I put on the case. Okay, yes. Send me. Yeah, for that.
Thank you.
The root 5 is positive, the number of root 5. 2 positive, 1 negative.
I think it's positive. No, the negative is very
Yeah.
Alright?
So, okay, what do we put in the overlapping space? We put how many dots and how many cross? One dot, one cross. Yes, 1 dot, 1 cross, please. So dot, cross. Yeah. What about
two on the hand.
on the top? Yeah, at the 12 p.m. position. Okay, for nitrogen. Yes. Okay. So that's how you will satisfy nitrogen and hydrogen. So they are all stable now. You see. So this is stable, stable, stable. Everybody is stable. What about NH4 plus? Okay, do you all remember NH4 plus? What do we call this ion? We learned this in the ionic compound chapter. We have learned a few ions. If you don't remember this, let me refresh your memory. So there were some ions that we discussed. Okay, where is it? Like the NH4 plus. I think it's a while ago. Oh, here. Do you remember this ion? You see NH4 plus. Here, ammonium ion. Okay, what is the structure of ammonium ion like? Okay, so now we are going to draw it. Don't confuse ammonia with ammonia. Ammonia is NH3. Ammonium ion is NH4 plus. Okay, they sound similar, but they are not the same thing. Okay, so to draw ammonium ion, we react NH3 with another H plus. Okay, so let's see what happens. Another H plus. Okay, so what is H plus ion? Do you remember what does having a positive ion mean? Does it mean it has lost or gained electron? Positive ion. Lost. Okay, so a hydrogen ion has no electron. Because a hydrogen atom has 1 electron, to form an H plus ion means to give up the electron. So it will become H plus ion. So who can donate the electron pair now? Look at the N. Can you see the N has a lone pair that is like free to donate to the electron division hydrogen? You see hydrogen ion has nothing in the outermost shell, which means it's not stable at this moment. Hydrogen is not stable right now. So how can nitrogen here help? So it can help using the lone pair. Okay, so we call this the non-bonding pair. So you have 3 bonding pairs here, and you have 1 lone pair. So can you help me label the electron pairs? Electron pairs found between atoms, we call them bonding pairs. They cannot be used anymore because they are involved, okay, in a relationship between the 2 atoms. They are, however, electron pairs that are, free, okay, or available. So we call these non-bonding pair. Non-bonding pair, they are also known as lone pair. So lone pair. So these are not used in bonding, but that doesn't mean that they cannot be donated, okay, by nitrogen to hydrogen. So put down this label first, and then we will look at how nitrogen helps this very unhappy hydrogen gain stability. So the nitrogen would come over. So let me copy this over first. So the nitrogen would come over, donate both of its electrons to hydrogen, okay, and you'll see something like this. So this hydrogen is finally part of the family. So you can see here. So hydrogen is finally part of the family. And thanks to the generous donation, okay, by the nitrogen, it has now a full shell. And what do we see now? We have ammonium ion. So can you write an equation describing what? This is H plus, this is NH3. Together they form NH4 plus. So this may be one of the first equations that you will learn to write in Form 4. So write down NH3 and H plus gives NH4 plus. Okay, so are you all convinced that this is stable now? Why is it stable? Because everybody has a full shell, right? Yeah, but before this reaction even happened, okay, H plus is not stable as it doesn't have a full shell. So you may want to draw like some sad and happy faces here. So this is certainly unhappy right now. But then nitrogen is here to help. So it says, oh, I have something spare anyway, so why don't I donate it to you? And this special bond in here, we call it dative covalent bond. So how many bonds in NH4 plus are normal covalent bond? How many bonds in here are normal covalent bond? 3. These 3 are normal covalent bond because they are contributed equally by the 2 bonding atoms. You can see that from the different symbols in here. But then there's a special bond that has symbols only from one atom. This is a special bond known as dative covalent bond. Yeah, I think you mix up lone pair electrons and dative covalent bond. Before the bond is formed, this is non-bonding electron, right? So non-bonding pair. But once the nitrogen has donated this electron pair into this shared region here, this bond, we now call it a dative covalent bond. Yes?
So when the X
Yes?
not done as not always.
What was the Oh, the dot and the cross, they are electrons from the 2 atoms. From the 2 atoms. The dots and the cross are to show you where they come from. Remember, we defined the symbols. Dots means they are electrons from nitrogen, if you can put it out. Dots means electron from nitrogen. Cross means electrons from hydrogen. Remember the definition on the left? When the bond is formed by equal contribution from the 2 bonding atoms, it's called a normal covalent bond. But when the bond has electron coming from just one of the atoms, the other has nothing to contribute. We call this dative covalent bond. So do you see the difference between these 2 types of bonds? So can you put down how many bonds do we see in here? 4. How many are normal? How many are dative? 3 are normal, 1 is dative. Okay. What about in here? How many bonds do you see?
3.
3. How many are normal?
3.
4 are normal. Yes. Okay. So can you put down NH3 has 3 bonds, and all are normal covalent bonds. Okay. So all are normal covalent bonds. What about NH4 plus? We say NH4 plus has 4 bonds, but yeah, out of these 4 bonds, 3 are normal. 1 is dative. Okay? So we can convert this into a more easy to read diagram. As this is so hard to read, NH3. This drawing is so difficult to read. Okay, so we'll draw it as N, 3 line, and an H. Like that. Okay, so N and draw 3 H's on the side. And draw 3 lines. The 3 lines represents the normal bond. What about NH4 plus? How many do we draw in a normal line? How many do we draw in an arrow? 1 in an arrow, and the other 3 we draw it as a line. Okay? And don't forget a bracket. I still see that some of you forgot to put a bracket when you figure out the charge. Look at ions are charged. You have to put a bracket and a charge. Okay? Right. So, is it clear? Yes. Is that clear? Yeah, you have to make it sure. Okay? Yeah, 4 bonds. 3 are normal, 1 is H. And then we can move on to the next part. Okay, so the next part is on the properties, okay, of ionic. Okay, wait. So remember, today is the deadline for submitting this homework. If you still do not turn this in, our ideas submission, okay, and then you will get 0 for this homework. It will be great, okay. So on the next page, we look at okay. Let's go back to where we stopped last time. We discussed some properties of giant ionic structures. Okay, the first being they have high melting and boiling point. So what are other properties of ionic compounds that you can think of? Just look at salt. What other properties can you think of salt? When you put it in water, do they dissolve or do they not? They dissolve. Okay, so most are water soluble. Put down the second green point here, the major green point here. Most are soluble in water. Yeah, and why is that? That's because water, you might not know this, but I encourage you to do an experiment tonight. Like open the tap, okay, and then let out a very, very narrow stream of water. It has to be very narrow for this experiment to work. And then grab a cardigan, okay, the cardigan or your scalp, okay, just rub it like to introduce a steady charge onto your scalp. Okay, so let's say this is your scalp. So you have rub on it like vigorously, okay, to give it a charge. When you bring the scalp close to the narrow stream of water, watch what happens. The water column, it will be deflected. Like that, you can try. Before you put the scalp next to the water column will just go downstream. But as you bring the scalp with a static charge on it, close, you will see that the beam of water will deflect very, very slightly. Very, very slightly. Okay, so if you don't see this at home, that's because the column of water might be too thick. You need to make it extremely narrow for this to work. What does this experiment show? It shows that water has like a regions of positive and negative charges. Okay, so can you like draw this diagram like really quickly? So we have a rod with charge, let's say positive charge. It will work also with negative charge, doesn't matter. When you bring this close to the water column in here, it will deflect towards the charge rod. Why is that? That's because when you look at it very, very closely, you see that water has 2 ends. Water has an oxygen end and a hydrogen end. The oxygen end is negatively charged. The hydrogen end is positively charged. So this is why the column of water, it will be drawn towards the charge state. Okay, so you have the negative end in here, and then you have the positive end in here. Do you remember that opposite charges attract? Opposite charges attract. So this is why it is the oxygen that gets drawn to the stick, to this rod in here. And therefore, the column of water deflects itself. So why am I drawing this? Okay, why am I telling you this? What does it have to do with ionic compounds being soluble? Well, when you add salt into water, the same thing happens. So can you draw a teaspoon now? So when you add salt, do you remember what is that L word that describes a regular arrangement of stuff? It's the lattice. Yes, do you remember this lattice? An ionic lattice. A regular arrangement of ions. In a sample of salt, you see many of these ions, okay, arranged very tightly. But then when you add it into water, what happens? They dissolve, okay, they dissolve. And why can the ions dissolve? That's because water can surround itself, okay, around these ions. So I'm going to draw a beaker in here. So you see a lot of H2O in here, H2O. Don't forget that the O is negatively charged, the H is positively charged. What happens? Next is that the ions, they will then become separated, like this. Okay, so you have O, 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 O. And then you have the H's around the negative ion. Can you tell me why wouldn't the H2O orient itself in the opposite manner here? That's because what is the charge of H again? H is positive, right? So something positive should go near something negative, right? Yeah, so this is why they are facing the ions in a special orientation. The O faces the positive side. Why not the H's here? You can see that they are opposite in direction. That's because O is negative. Something negative can only interact with something positive, right? So there is a reason. I'm not drawing it randomly here. So if you have two highlights or blue and red pen, I want you to paint it in these colors. So, and by so doing, you are separating the ions. You know when the ions get far enough, you will not be able to see the salt again. Okay, so at the very beginning, what do you see in here? You see a white solid, right? Yeah, because the ions are very close together, so you can see a solid. But when you put it in water, the ions, they will become separated. Okay, so you see, think of this water as like some security guard. Okay, they are separating two guys now. These two guys, the positive and the negative ions, they cannot come back together. They become so far apart. Now, you have a colorless solution. Okay, so this is why we say when you add salt into water and you stir with a glass rod, so let me add a glass rod here, you will get a colorless solution. That's because the ions become far enough now. Okay, so can you write down white solid NaCl will become a colorless solution of NaCl. And inside this solution, okay, write down what AQ stands for. AQ means aqueous, means it dissolved in water. Okay, something dissolved in water. What about bracket S? I think you guessed it. Bracket S means solid, right? Okay. This is why this is happening. White for this. Okay, anyway. So you have S for solid. You see the S here for solid. And AQ for aqueous. Okay, aqueous means something has dissolved in water. And can you see that the ions are now separated? Yeah, because the ions are separated really, really far away, you cannot see the salt anymore. It becomes dissolved in water. Okay, so don't use the word disappear, use the word soluble. Okay, in water. You say salts are soluble in water. Don't say salt disappear in water. Okay, right. That's the second property. The third property, you can also explain it, okay, and you can experiment with it. When you put some salt grain in your hand and you apply a force onto it, do salt grains break easily or do they not break easily? They actually finish. They break easily. Okay, so can you put down they are brittle. So they are brittle and hard. Okay, so they are hard and brittle. That's because at the beginning, the layer of ions, remember we call this a lattice of ions, okay? You see oppositely charged ions next to one another. When you apply a force, you are moving one layer relative to the other. Can you tell me what happens now? Between these ions, do you have attraction or repulsion? Attraction. Okay, so can you use two different colors in here? Orange means attraction. What about on the right? As you shift one layer off to the side, what used to be attraction will now become
Retracted.
repulsion.
repulsion.
Oh,
Repulsion. Okay, so use this word now. So repel. You see, light charges repel. So can you put down repulsion here? So this is why, while they are pretty hot, okay, they are also pretty brittle, meaning they break very easily. Okay, so you can just write down when a force is applied, this is what happens. So when a force is applied, you will shift the layers around. And when the layers shift around, what used to be attraction will become repulsion. Okay? So just write this down and then we'll continue. So opposite charges attract. But like charges, they repel, right? Right? So opposite charges attract and like charges repel. So attraction becomes repulsion. And so the structure changes. Okay? So attraction becomes repulsion. So therefore, the structure changes. Is that very clear? Yes. Okay. So we'll pick up from here next time. So remember to turn in your, if you do not turn in by today, 0 for this grade of homework. Okay?